Thanks, Ajay. Yeah, I'm actually going to work off a lot of things that Sarah said. That was an excellent talk, and you just set up all sorts of problems for me, so this is great stuff. What I'd like to do today is concentrate more on sort of the timing of chemical processes. I went over the introduction a bit yesterday, so what I'm going to do today is go into some more detail about the timing of these processes. That's the plan, and then Bill McDonough tomorrow is going to cover more of the chemical processes that I'll be outlining the chronological timescale for today. So I want to give you some of the background systematics of how we get the timescales on core formation, planet formation, and the like, giant impacts times. So this is the introduction slide. I'm actually going to go back. I started yesterday in this phase when we had everything vaporized in the solar nebula, and I'm actually going to go step back in time back to this phase because it brings in some important components that both are used for tracers for the initial chemical heterogeneity in the solar nebula and also the chronometers that we need to use to determine these processes. So one of the things we know, yesterday I started with the story with everything being volatilized in this inner parts of the solar disk. We know that that's not completely true because there are grains that survive that period of time. Here's one of them. This is a silicon carbide grain. The size scale microns. So these are on the order of half a micron to 10, maybe as much as 10, 20 microns in general. These are present at about the part per million level in a number of primitive meteorites. The interesting part about these grains is that they're not from our solar system. This is condensed in the outflow of some other star that came in. We even know what type of star it is because we can measure the barium isotopic composition in this. I'm sorry, all the non-chemists, but so this is the way we look at this. This is the mass of barium down here with the isotopes of barium. On this plot, we're looking at the silicon carbide barium isotopic composition divided by some terrestrial value. And by terrestrial value in this case, on this kind of a scale anyway, basically everything in our solar system would fall in that nice horizontal line there at 0. So if it were normal terrestrial barium or lunar barium or Mars barium or whatever, it would fall within the width of that little line. So you can see here that this is dramatically different. So it's terribly depleted in 130, 132, 135, and 137. Now, the interesting part about this is more in the realm of stellar nuclear astrophysics because this is actually tracking nucleosynthesis. So these isotopes are made by different stellar processes. P process is where you're turning neutrons into protons in the nucleus. S process is where you're adding neutrons on rather slowly, and you're sort of fighting the decay as you become unstable by adding too many neutrons. And then the R process here on the neutron-rich side is where you're dumping in neutrons so fast that basically you can't decay fast enough, so you're building elements way out in extra neutron space. To get to things like the R process, you're talking about supernovas, so large, high-mass, energetic stars undergoing high-energy end-of-life events like an explosion in a supernova. S is probably occurring in still big stars, but not quite so big, these things called asymptotic branch stars, which is probably the source of these kind of grains. So the reason for introducing this is partly that these kind of isotope anomalies are tracers of the stellar contributions to our solar nebula, but also to point out that these survive. So these are found in meteorites. So not everything that was present in the solar molecular cloud got evaporated during that early high temperature phase. These, for the purposes of this discussion, really, these can be used as tracers of the chemical characteristics in the solar nebula. What's being shown with more and more isotopes being added to this is that there are isotopic differences between a number of elements according to meteorite groups. So here's a series of plots from a nice paper by Paul Warren. By the way, sooner or later when I get the wiki site up, I have all the PDFs of all the papers that I'm presenting in these talks, so they'll be available for you to take a look at if you're interested. These are plots of 54 chromium, 62 nickel, and 50 titanium. It's 54 chromium again. The thing that these isotopes share is that these are all on the neutron-rich side of these elements. These elements are all close to the iron peak. They're all made in the same nucleosynthetic process. In this case, it's called the equilibrium process. This is a process that also occurs in supernovas. It's a case where the temperatures are so high that you're dumping on neutrons really fast, but at the same time, the temperatures are so high that these things want to go back to iron 56, which is the most stable nucleus. So there's competition between adding neutrons and losing neutrons to get back to iron 56. What you end up with then is a bunch of neutron-rich isotopes like 54 chromium, 62 nickel. Again, the point here is that these are tracers of chemical characteristics. So if you look, all the carbonaceous chondrites, and Bill will do a lot better explanation tomorrow what we mean by carbonaceous chondrites. But they lie out in fields like this here on this is titanium chromium. They lie way out here, whereas the Earth and Moon are down here. Other types of meteorites, these are the ordinary chondrites, the HLL-E chondrites are in here, Mars is in here, Angrites are a type of differentiated meteorite, HEDs are they're basaltic meteorites, some differentiated planetesimal. Urialites are a very reduced type of meteorite. So the point being is that what we're looking at here is that these isotope anomalies are tracking species basically in chemistry in the early solar nebula. And what we know from this is that the Earth is not well represented by any one group of these meteorites in particular. So when somebody tells you the Earth is a CV chondrites are here, the Earth is down here. So that's not possible. What is possible is that they could be mixtures of many of these. So you could see, imagine in a diagram like this, is that maybe the Earth is a mixture of ordinary chondrites and carbonaceous chondrites. So you see it's pulled off in that direction. Yeah?
Yeah, I wanted to say there's also a possibility that the molded material that formed the Earth is actually represented at all in the current.
That's, I mean, like Bill said earlier, yeah, I mean, these are the meteorites that we've gotten delivered to us on Earth in the last, few million years or so. So they do not necessarily represent the stuff that was around to build the Earth. That's definitely true. But the point being is they don't perfectly represent it. So when we're talking about chondritic models for Earth chemical composition, you got to be aware that there are these issues with these kind of models. What's that? Age. Oh, EH, yeah. I mean, this will show through in a few things. In isotope space, the ansitite chondrites actually fit pretty well. In chemical space, they don't fit so well. So Bill will cover the chemical side of that argument tomorrow. Right. Alrighty. The issue with this, so one of the troubles that we're having, this is in 2011, so these isotope anomalies are only being discovered now. So, this is really a breakthrough front in this field, is we're actually being able to resolve these type of isotope anomalies. And the key question that still needs to be answered is we actually know where these 54 chromium anomalies come from. We found them. They're little chromite grains that are about half a micron in size that carry huge 54 chromium excesses. These, again, are the type of PreSolar grains I showed you in the silicon carbide. So the question is whether these little microscopic additions to the chondrites actually determine their composition. They probably don't because there's such a small component of them, or whether they simply track some compositional variation that was present in the solar nebula. So one of the options for this is that the 54 chromium excesses are the sign of the supernova component. So one of the possibilities and one of the models for the collapse of the solar nebula in the first place is that there was a shock wave from a nearby supernova. The shock wave came in and started the molecular cloud to condense until its own gravity took over. And given that these equilibrium process isotopes are the ones that show these chemical differences between the various types of meteorite groups, it's clear that they were not perfectly homogenized within the solar nebula prior to the formation of these meteorites, whereas something like the silicon carbide probably was. So this is an example maybe of the grains that are from the star that started the history of the solar system. And they may be tracking the chemistry as they came in. Now we've known for a long time that the Earth doesn't have the isotopic composition of meteorites. This is from Bob Clayton's summary in 2004, but I think this data dates back, probably the 60s or 70s. So this is a three isotope oxygen plot. This is 17 to 16 ratio, the 18 to 16 ratio. This is relative to mean ocean water, so 0 is short here in Santa Barbara in the water. What happens on diagrams like this, oxygen isotopes, there are all sorts of nucleosynthetic processes that can modify them, but they also undergo fractionation during chemical processes. But the fractionation that occurs during chemistry follows what's known as a terrestrial fractionation line here. That's this line. It is very mass dependent, so that the fractionation that's seen in 18-16 ratio is twice the amount that's seen in the 17-16 ratio. So it's purely mass dependent. And on a diagram like this, it provides this slope half line. There's the ansitite chondrites here, which again gets the issue of the overlap of ansitite chondrites and Earth. The Earth falls along this line with the mantle being in here and biology being way down here and various other things. There's CIchondrites up here. Most of the ordinary chondrites lie above the line, and then there are the carbonaceous chondrites that actually track well below the line. And they track well below the line, not on this slope half line, but on a slope 1 line. And in the old days, before we appreciated the alternative explanation for this slope 1 line, one way to get this is to add Puro-16, which can occur in some nucleosynthetic processes. So this was initially interpreted as tracking nucleosynthetic anomalies, where you're adding Puro-16 to probably a solar composition up here and making these funny carbonaceous chondrites sort of drag off the line. But what we know now for probably 20 years is that there are almost always UV-related photochemical processes that don't care about the mass of the isotope when they're doing chemistry in a gas phase. So you can get a slope one line. Basically, the magnitude of the effect is the same in 18 as it is in 17. And you can create these slope one lines through like a UV irradiation of the early solar nebula. So this doesn't necessarily have to be nucleosynthetic. In fact, we're pretty sure it's not anymore, because in all these fields, I think Dave put it well yesterday, is that the Earth is really the sawdust on the floor after you form the sun. So it's really sort of the leftovers. And we used to think that the Earth, is our home and it must be solar and oxygen isotopic composition. But this was thrown away when Kevin McKeegan actually measured the oxygen isotopic composition of the sun based on solar wind that was implanted in the Genesis spacecraft. So what he found is that this is actually way off of this plot down here at -60, -60. It's down the slope one line. So instead of the Earth being solar here and these being just funny rocks affected by some small nucleosynthetic components, what's really happening is that the sun is way down here. The Earth is very different from solar isotopic composition here. So how did it get up here? So the only thing that we know, so if this is the main mass of the solar system down here in the sun, how did it get up here? One of the things that lies up here that we know from meteorites as well is the interaction products, basically weathering minerals from meteorites that probably had ices present in the early solar system. So these maybe, you can think of them maybe as cometary ices. I think of them as the ices that were present in some carbonaceous chondrites. So what we're looking at here then is in a major element like oxygen. So we're not talking about funny trace elements anymore. We're talking about one of the most abundant elements in the Earth. That we have an isotopic composition that's very different from the sun, and it shows that it's some sort of a mixture between solar and some very evolved isotopic component in the solar system, maybe even the volatile component. So this is an important point to note, is that we're looking at an Earth that's a very distinct composition compared to the sun. I mean heavy in terms of its oxygen isotopic composition. Sorry. Yeah, I mean just with plus 180, plus 180, it's way out the line. It may have different D abundance, HD ratios too, but we won't go there. All right. So that's just to leave with you the understanding that we're not starting with a homogeneous nebula to begin with. So keep that in your mind as we go. This is the plot that I showed yesterday about the condensation sequence. So we know that this is probably true for reasons that I'll show you in a second, is that things were hot. They just weren't hot enough to vaporize things like silicon carbide or these little chromite grains that carry the 54 anomalies. So I mentioned this, as you cool things down, you're going to start condensing the highest temperature elements first. You get down here to calcium and aluminum. We'll look at some meteorites that actually contain phases rich in those, and then down to the main components here, magnesium, iron, and silicon, and then to the volatile components further down in temperature. And this addresses a question that came up in Sarah's talk, actually. So here's a slice of this is a CV chondrite. CV chondrites they're carbonaceous chondrites, but they're actually volatile poor. They've been subjected to metamorphism, and they've lost whatever water they used to have. But this is an example of this accumulation phase of planetary objects that we've sort of been hinting around. All of the accumulation models we're talking about start with planetesimals that are 100 kilometers in diameter or something. But what you've got here are actually grain sizes. These are probably millimeters to at most a centimeter. And you've got here, this is a calcium aluminum rich inclusion. So these little white things, there's another one up here. These little amoeboid things are actually almost entirely made out of the type of grains that would condense from a very high temperature solar nebula. So alumina, the hibonite, calcium, titanium oxide, plagioclase, these minerals that you would expect are basically ceramics. So these are the high temperature component condensing out of the solar nebula. They've been isolated into these sort of millimeter to centimeter sized aggregates. There's actually many grains within there. But so these little phases. So you're looking at things that are actually present as individual dust grains or dust balls in the solar nebula. There are these other things here, these little round guys known as chondrules, which of course are what give chondrites their name. These are little molten droplets that were free flying in space. So they're basically millimeter to centimeter size melt droplets in space that cooled and crystallized as olivine and pyroxene. So these represent, again, the main mass elements that are present in the Earth and in terrestrial planets. So you've got high temperature, you've got the intermediate temperature stuff here, and all this grunge in the middle here are fine-grained, low-temperature condensates. In a more hydrous meteorite like a CIchondrite, these would be things like serpentines and like. So they would be carrying lots of water, basically clays, if you will. Serpentines, clays, brucites, OH-bearing minerals are in this matrix. So in this thing, I don't know what the size this is. It's probably, maybe this big. What you've got here are millimeter aggregates of everything that I showed you in the condensation sequence last time. The high temperature CAIs, the intermediate major elements, and the chondrules here, and then the matrix that's carrying all the low temperature materials. Yeah?
Is there a reason why CI are not circular? The chondrules are circular?
There probably is, but I don't know what it is. It's a good question. They're often like this. One of the things that you actually see with these in occasion is that they've got a rim around them. So they've formed, and then they're very high temperature objects. They were interacting with the solar gas. So they're rimmed by something that's circular. But yeah, they often have these amoeboid shapes, but I don't know why. Yeah.
I think it's because chondrules have been melted.
Chondrules are round because it's a free energy minimization. You've got a liquid droplet. And these probably are just dust balls. Yeah.
If you look at CIs, they've been melted. They're round.
Yeah, okay. Yeah. Thanks. All right.
What is the ratio from the total mass between those three groups?
Well, so that's an issue. So if you think about this, and we go back to the stage of planetary accumulation before we were dealing with 100-kilometer diameter planetesimals, we're dealing with millimeter-sized grains. What a meteorite like this has been able to do is assemble these various low, medium, and high-temperature components into a composition that basically is solar. So if we look at CIchondrites, thanks, you led into my next slide. Appreciate it. So this is then a composition of a CIchondrite, which is the chondrites that are closest to solar in composition. This is the whole periodic table, so don't bother about reading it. It's every element down there. But the point being is that what you have here is relative to the sun. So this is the sun divided by a CIchondrite. Basically, for all of these elements, you have solar abundances in CIchondrites that are within certainly a factor 2 or so, maybe even better, of the sun's composition. The only ones that aren't are the real gases, nitrogen, carbon, and of course the rare gases, noble gases aren't shown in this diagram. Hydrogen's up here, factor 10 to the 6 or something, so they're outrageously enriched. Lithium is consumed in nuclear fusion in the sun, so that's why it's deficient in the sun here. But the point being is, getting back to your question, so you're thinking about these millimeter grains that individually sampled as very discrete parts of this condensation sequence, and yet they've been assembled into this meteorite in the correct proportions in order to give a composition very similar to the sun. So we're talking about mixing phenomena, and this is, I think, a perfect one in terms of the evolution of a nebula. You have these discrete components, but you manage to mix them in the solid state to get back to a composition that's basically the average of the starting composition. This is a solar photosphere, yeah.
Any indication of that could be different within the sun?
Well, yeah. I mean, this is basically photometry of the outer sun. So there could be compositional gradients within the sun. I think the reason that you don't really expect them is there's lots of convection in the sun. So one would think that the outer gaseous phase of the sun might be representative of its composition. But yeah, it's an issue. In fact, I think the element concentrations are better known in the chondrites because they're much easier to measure. Certainly some of these trace elements are not very visible in the spectrum of the sun. So there's large photometric errors associated with some of these trace elements. What's that? It's only from optical spectrometry, yeah. In the sun. All right, so one of the other things, though, that came in with these supernova components or these PreSolar grains is this whole list of short-lived isotopes. So these were newly synthesized in stars and injected into our solar system. So here's a list. These are the ones that are actually in use. There's a variety of other ones that have been found, even some just shorter half-lives. But the importance of these is that they provide an incredible chronometry because there's many different types of chemical species here, from gases. These two decay into xenon, for example. So they're particularly good at looking at this is a refractory plutonium going into a noble gas. There's others, samarium and neodymium, are only fractionated by partial melting, so you can track chemical processes like partial melting. Hafnium and tungsten, as we've seen, and we'll see some more, is primarily affected by metal silicate separation. So this table then gives you the ability to investigate condensation, volatile loss, metal silicate separation, and silicate differentiation in a planet. The beauty of these is that the half-lives range over the time interval of interest here. So Dave mentioned when he showed the time of formation of the solar system on a log scale, we're looking at a lot of the interesting stuff in the solar system happening on 1 million year to 10 million year to maybe 100 million year time scales. And it turns out, that these type of half-lives are perfect to provide high precision chronometry in that period. Okay, the systematics are pretty simple. It's the standard radioactive decay. It's a probabilistic theory where you have a decay that goes exponentially according to some decay rate here. It says lambda 2 over the, or log 2 over the half-life times the time interval. Start with some number of atoms to begin with, and you end up with a lower number after this decay interval. Usually it's easier, instead of looking at the decay of the parent, is to look at the ingrowth of the daughter. So you start with a daughter today is equal to whatever daughter isotopes were present at the beginning, with plus the contribution that you get from the decay of the parent isotope. And you can go through the math. It's very simple math. You end up with a standard decay equation here, and expressed in one of the systems, rubidium strontium here. So you measure the strontium isotopic composition today. You normalize to a stable isotope of strontium just because it's easier to measure ratios than the absolute abundances. So today is equal to what the ratio was when it started. The parent to daughter ratio here today, because this hasn't changed much, times this, the time factor here. So you plot this on a diagram with samples with different rubidium strontium ratio. You get straight lines. The intercept is the initial strontium, and the slope gives you the age of the rock. So they're very simple systematics. This is a long-lived system, though, because here this has a half-life of 50 billion years, so it's still around. You can still measure it. But when you're dealing with extinct isotopes, this is 0. Like extinct, I mean they're not here anymore. So you can't measure their presence in the present day. So you have to go to slightly different systematics. So here's one. This is the same type of systematics for aluminum-26 decaying to magnesium-26. This has a 730,000 year half-life. So it was present during this sort of million-year interval that we're interested in early planetary history, but was long gone. It was gone quickly. So you look at it, magnesium-26 is the daughter. You normalize to some stable isotope. So whatever that ratio is today is what started with at the beginning, plus what's been contributed by aluminum decay. So aluminum-26 relative to 24 magnesium. But you can't measure this today because this is gone. So you have to replace this with something like this, where you go to aluminum-26 to 27 ratio, this being the stable isotope of aluminum, times the aluminum-27 to magnesium-24 ratio. Both of these are stable isotopes, so what you measure today was what they were back when the process you're interested in dating was occurring. And this then becomes the unknown, is the 26 ratio. This is the extinct nuclide to the stable isotope of 27 aluminum. So you can go through that. And if you plot this then, you can measure this today. You can measure the aluminum-magnesium ratio today. So you plot those two on an isochron diagram. You get an initial that's the magnesium isotope composition to begin with. And you get a slope that isn't directly the age. The slope is in fact this, 26 to 27 aluminum times the decay of the aluminum. So you can't actually get absolute ages from this. You can get this ratio. And this ratio, though, if you know that at some time, so if you know the aluminum-26-27 ratio in the solar nebula at some time, and you know it provided from your isochron here, you can then solve for the time, or the time difference between your reference age and the age of the process you're interested in. Yeah?
So how do you know this 26 over 27 the reference?
This one. I'll show you. That's the next slide. So you need to know that. So there are two things that are important in working with extinct nuclides. One is that you need to have a reference, and you need to know it reliably, and you need to correlate this with some age that can be determined by some other means. And we'll see that that's almost always the uranium-lead absolute age dating system. The other thing that you need to know is that this isotope was homogeneously distributed in the solar nebula. So one of the issues, if this is being injected by a supernova and wasn't adequately mixed in, then this ratio may change, but it doesn't change because of time. It changes because of position in the nebula, or percentage of the supernova component, if you will. So both of those assumptions have to be checked. And they are checked quite routinely, and I'll show you some examples of how all that works out. So the beauty of this, though, besides being able to use this whole family of radioactive decay systems to investigate all these processes that you're interested in, is that you can get incredible temporal resolutions with these systems. So here's an isochron for calcium aluminum-rich inclusions in a variety of chondrites. They define this very nice line in this plot of delta 26 is this is the 26 to 24 ratio, but it's represented in per mil. Just, I mean, these variations aren't really very big. So it's the 26-24 ratio versus the aluminum 27 to 24 magnesium ratio. So you get these beautiful lines. From that line, you can get a slope that's 5.85 plus or minus 0.05 to 10 minus 5. So that gives you the abundance of this isotope when the aluminum magnesium system in these calcium aluminum rich inclusions closed. Now, so we'll get to what that actually means and how you interpret that as an age. But what I'd like to point out is that this kind of an error on this slope corresponds to an age uncertainty of 9,000 years. So we're looking at an event that's 4.5 billion years ago that we're able to get 9,000 year precision on the chronology. Now, you know, important to keep in mind, precision and accuracy are not the same things. But once we get the accuracy worked out, you can get just, you know, stunning precision, age precision on these events. It's hard to get 9,000 year precision in, you know, rocks from the Cascade Range that erupted 1 million years ago. So we have the opportunity for very precise age dating of events occurring very early in Earth history. Now, turning these into time, though, gets to comparisons like this one. These are a variety of looking at calcium aluminum inclusion ages from a variety of methods. So one is you can date them with absolute uranium lead systems, so lead ages, and you can see here there's a range in ages of on the order of 1 million years, going back to 4568 to 4567 million. So that's the kind of age range that you get looking at them from just uranium lead. There's been questions about whether that represents the formation time scale of CAIs. In fact, what we've found recently is that the uranium isotopic composition wasn't constant in the early solar system. So this may in fact be a sort of a nucleosynthetic effect, if you will. So we're still working on refining that, but the important point here is we're looking at like a 1 million year age gap. And then these are the ages from, this is hafnium tungsten here, there's magnesium chromium, aluminum magnesium, other ages. You can see that these actually agree quite well, about 4568. These are all referenced to this igneous rock. This is an angrite, it's called. It's basically a pyroxene-rich gabbro. So it's some early planetesimal melt. It has a very accurately determined uranium lead age, and you can measure aluminum, magnesium, manganese, chromium, and hafnium tungsten ages on it. So these are the kind of things that form reference points. So if you use this as a reference point, this is the age range that you get for calcium aluminum rich inclusions. So what this is telling you is that with these short-lived radioactive systems, you can get precisions of 9,000 years, and at our current level of accuracy, you might be talking about plus or minus 1 million year. So that's the level of precision that we have going into these systems. So we can then start asking what was going on in the early solar system at these kind of chronological time scales. So here's an example. This is a different angrite. An angrite is just a volcanic rock on some small planetesimal. Like I said, it's basically a pyroxene-rich gabbro or a basalt, if you will. Not quite, but close to that. It can be dated by uranium lead to 4564. Here's Dorbany is just the name of the meteorite. This is another one of exactly the same type, Sahara 99. A lot of these meteorites are found in the dry deserts of northern Africa. So this is hafnium tungsten. You get these nice slopes. This is manganese chromium. You get a nice slope here for Dorbany as well. If you compare the ages for these systems, again, it's the uranium lead that seems to be off when these are referenced to, this is the Lewis-Kliss angrite, I think. But you're looking here at the short-lived isotopes agreeing to within a fraction of 1 million years, and this may be offset because of this uranium isotopic composition issue I was discussing. So what this is telling you is that within let's say 1 million year precision, you've got the same age of these angritic meteorites, and this age is within something like 4 or 5 million years of the calcium aluminum rich inclusions. So from the time you went from forming 1 millimeter diameter aggregates of calcium and aluminum, these refractory solids, you've grown a planetesimal big enough to undergo melting, make a basaltic melt and erupt it on its surface and crystallize it. So what we're looking at here is the evidence that planetesimals form quickly, and within a couple of million years, 4 million years, say, they not only form, but they grew big enough to melt and differentiate. What this is telling us is it's probably likely that the Earth formed out of differentiated planetesimals rather than these chondritic objects. So by the time the objects got big enough to become these oligarchs that Sarah was talking about, they probably did have cores. You notice all of her movies had cores in the middle of the impacting objects. That's probably true. So what was coming into the Earth as impactors were already differentiated objects. Yeah?
How do you know what you see as a localized impact melt?
Well, first off, these have anhydrites have a very strong depletion in siderophile elements, so they would not be associated with impact melt because impact melts probably are chondrites have brought in siderophile elements. There are other types of meteorites like eucrites that are both volatile and siderophile element depleted. They look like partial melts of planetesimals, and they all give ages of this kind of a range. The other one that you can look at, so this is melting. So this is melting on the shallow silica portion of a planetesimal. The other side of it is you can looking at melting within the planet, the formation of cores. So this,
How big does the planetesimals have to be?
So the question is what the heat sources are. One is impact. So one of the possibilities of melting is impact. The other likely one, given these kind of timescales, is heating by aluminum-26. So besides forming a great chronometer, it's a major element. You're having this short half-life decay, and it's providing a lot of heat. And there are models that show how big you have to be before you get melting, and I think it's, anybody knows, it's like 50 to 100 kilometers. You need the object to get big enough so that it can't radiate the heat that is generating inside. And I think that occurs on the order of 50, 100 kilometers. So these do not have to be really big objects to undergo this type of melting.
So, back for us seismologists, and why do you have to involve melting in this?
Because this is a melt. This is a volcanic rock. So this is a partial melt. This is basically a basalt. So this is a melt of some ultramafic planet. This one is this is a group of meteorites called anhydrites. They're all basically basalts. There are other types of basaltic meteorites known as eucrites that give very similar results to this. So their composition says that they are partial melts of some peridotite composition. If you think of a chondrite as a peridotite, that's a pretty good analogy, plus iron. But so these are melts of some chondritic planetesimal, if you will. Yeah. Yeah, no, I mean, there's been a lot of work looking now at the 235 to 238 ratio, and the answer is a lot of these early rocks, it's not the same as we've been using on the Earth. In fact, the standard value that was used for decades on the Earth isn't really correct either. Part of this comes from the improved precision of isotope ratio measurements. So something that was set up as a standard in the 1950s and measured precisely for the 1950s is no longer adequate for the modern world. But if you look at the range in uranium isotopic composition that's seen in early solar system material, it translates to as much as 5 million year age difference in the uranium-lead system. And the trouble with it is it's much easier to measure lead than it is to measure uranium isotopic composition to the requisite precision. So it's just a technical issue in trying to resolve the uranium isotopic contribution to that age difference.
When it comes to MSWD21, that hasn't been propagated into the uncertainty, or it would be within uncertainty of these short-lived systems.
Yeah. No, I mean, that's an issue with the age character here, too.
You might as well tell somebody what MSW is.
MSW, mean squared weighted deviations. It's basically, I mean, well, it's an interesting parameter. It's if you actually put realistic errors on the points, it goes to 1. If it's 1, it's a perfect fit to the line. And if it's a big number, it means that there's scatter outside of the analytical error of the points. So 21 is not a statistically valid line. But I think if you look at those points, you would agree that it's not a terrible line. So Mark is right. Is that, I mean, this error probably does include this because this is an isoplot age, but
you take the square root of MSWD and multiply it by standard deviation,
yeah,
which
should give you the error. Yeah.
Make it within uncertainty coordinates.
Well, but I think this error already includes that.
No.
I bet it does. Yeah. Well, let's go through isoplot after this. I'm almost certain that it does. All right, so we'll move on. So we've looked at melting in the silica portion of the Earth, or planetesimals. This is an example that we were actually forming cores on planetesimals very early as well. This is the hafnium tungsten system. I went through a little bit of systematics of that yesterday, and I'll go through some more in a second here. But what this is this band here represents the tungsten isotopic composition that's determined for the initial tungsten in the solar system based on calcium aluminum rich inclusions. So So a lot of our story here relates back to this formation of this refractory component. What you see is that these are a variety of iron meteorites. Iron meteorites are presumed to be they're either directly condensed out of the solar nebula, or more likely they're the cores of planetesimals, and certainly some of the groups are. The 4As in particular are clearly magmatic. So what you've got here is that these are isotopically indistinguishable from CAIs. If you look at a time scale that this translates to up here, you can see that most of these formed within a million or a couple million years of CAI ages. So you're looking at core formation on planetesimals occurring in this sort of couple million year age range. There are some groups of iron meteorites that extend this out to as much as 20 million years. 20 million years is pushing it if you're thinking about aluminum-26 as a heat source. So it's likely that these might be the result of an impact into a planetesimal that got it hot enough to melt. But for these kind of things, I think the most likely explanation is that the planetesimals grew large enough where they could retain the heat from aluminum-26 decay. They melted, the iron came out the bottom, and the angrates came out the top.
I'll just add that the lowest one down there, Gibeon, is I think the 4A.
Yeah.
And cooling, the chemistry recorded in the cooling of the large grains inside this meteorite dictate that it had cooled at a certain rate, and from that they've argued that this planetesimal was 150 kilometer wide core.
And actually in this case, for that one, it actually, for the 4As, the argument, the cooling rates are so fast, the argument is it didn't have the mantle left. So this may be when you hit and run things, where basically the mantle was stripped off this planetesimal, leaving behind a metallic core. So this, I mean, there's a lot of modeling involved here. But basically what you're talking about is an early differentiation event, forming this core and then stripping the mantle off of it. Alrighty. So we'll go on now to this process of core formation. I showed you this yesterday. It got blown up and went fuzzy on me in the process. But I showed you yesterday how you can use the hafnium tungsten to get core formation. This is a plot versus condensation temperature down at this range. For elements that don't dissolve in metal, they would fall along here according to their volatility in this gray band. And then if they're soluble in iron metal, if they're siderophile elements, they plot below that band. So yesterday we looked at hafnium tungsten, which is a lithophile element that decays to a siderophile element. But we're going to add to this a couple of other ones now. Palladium silver is another system based on the 107. Palladium decays to 107 silver. These are both strongly siderophile elements. Palladium in particular is very strongly siderophile. The difference here is that both hafnium and tungsten are refractory elements. They have very high condensation temperatures. Palladium is fairly refractory. Silver is actually a moderately volatile element. So this is the Earth, sorry, yeah. Yeah, this is the Earth. Actually, you'd probably look like this in a planetesimal too, but this is the Earth. So palladium silver here is affected both by core formation because they're both siderophile, but it's also going to be affected by volatility. Then the other system we'll look at is the manganese chromium, which I talked a little bit about yesterday. These are not affected by core formation, but they're affected by volatility. So what we have by combining these three isotope systems is the ability to sort of compare and contrast the issues that we're talking about in forming a planet. Volatility, volatile loss, versus the timing of metal silicate separation and core formation. So if we apply the systematics to this is a simplified version of what I showed you yesterday for hafnium systematics. So you start with some chondritic initial tungsten here. It's actually, this is an old diagram, the estimate's up here now, but so this is moved up. If you have a chondritic hafnium tungsten ratio of 1, you follow this red line. If nothing happens to it, you just follow the red line until 182 hafnium is gone, and then this just goes horizontal for the rest of solar system history. If you form a core, all the hafnium stays in the mantle, so you stop making 182 tungsten in the core. So from that point on, the 182-184 ratio just goes flat. But in the mantle left behind, you have a high hafnium tungsten ratio, and you keep growing in that radiogenic 182 tungsten. So that's the systematics we went through yesterday. I explained to you some of the complications with, this is a one step of core formation. And of course, this is probably happening with every incoming planetesimal. Now, the palladium silver system has very comparable systematics, except it works in the opposite direction because in this case, hafnium is lithophile, so the parent stays behind in the mantle, but in the palladium silver system, palladium, the parent, goes into the core preferentially. So what happens, you look at a system like this green line here starts out with some initial silver isotopic composition, and you're working with a volatile rich meteor like a CIchondrite. The chondrite will evolve out along here along the black line, And then if you have a core forming event at 10 million years here, for example, you'll segregate it out, but in this case the mantle is the one that has its silver isotopic composition retarded because it has a lower palladium silver ratio because all the palladium went into the core. So here is the core, for example, because you've increased the palladium silver ratio in the core, and it rises up like this. So there's a few things that are worth noting. Hafnium tungsten has a half-life of 9 million years. Palladium silver has a half-life of 6 million years. So they have a different sensitivity to the timing of these processes. The other one, as I mentioned, is that palladium silver is sensitive to volatility. So if you start with a volatile-rich meteor like a CIchondrite, this brown band here is the precision with which we're able to determine the silver isotopic composition of the Earth's mantle. So in this case, we wouldn't be able to use the palladium-silver system to tell us anything about core formation. On the other hand, though, we know that the Earth is volatile depleted. So we work with a volatile depleted meteorite, like a CIchondrite, for example. The loss of the silver leads that chondrite to have an evolution like this. So then if you superimpose a core forming scenario like these on top of this, then you will produce a mantle isotopic composition that's outside the range that we actually measure for the Earth. The thing to note is that with the palladium-silver system, these ages in this sort of volatile depleted meteorite rise outside the range of the terrestrial mantle within less than 10 million years. So the palladium-silver system looks like it's forcing you into a very rapid core formation of the Earth, 10 million years. Yesterday I told you the simple single-stage evolution is more like the order of 35 million years for hafnium tungsten. So these ages aren't in agreement. But why aren't they in agreement? One possibility is that, in fact, the Earth didn't form from something this volatile poor. It formed something more volatile rich, in which case palladium-silver doesn't offer any constraints on it. So we're balancing out here volatility versus the timing of core formation when we look at these two systems. So the easy way to make palladium-silver longer, the age of core formation longer, is just to assume that the Earth formed more volatile rich. But if it formed volatile rich, if it formed from CIchondrites in the manganese-chromium system here, because this is only sensitive to volatility, it would lie out here, which it doesn't. So the manganese-chromium system shows us that the first stuff that the Earth is forming from was already volatile depleted, which then has implications for the palladium-silver system because it means the early material coming into the Earth had a high palladium-silver ratio, and hence the silver isotopic composition would rapidly evolve out of the range that we have for the Earth. So I know I'm confusing you with this, but the point being is that there are three isotope systems involved here that are sensitive to different things. They're sensitive to differences in timing, they're sensitive to differences in the time of core formation and the process of core formation, and they're variably sensitive to volatility. So combining those three together lets you resolve that into a model that looks like this. Do you want to ask a question first?
Yeah, I wanted to ask if this could be reconciled with multiple core-forming events.
Actually, I showed you yesterday with the hafnium tungsten is very sensitive to multiple core-forming events. And particularly this issue that got brought up a little bit today is the amount that the incoming core equilibrates with the mantle on the way through to the growing Earth's mantle. That's a difficult problem, and it is an important parameter in this. Turns out palladium-silver is less sensitive to that simply because the silver concentration of the mantle is reduced enough that the incoming material basically overprints it. So it's not as big a deal for silver, which is another interesting comparison between the two systems. So this is one model that can reconcile these three systems together. It starts out by accreting a volatile poor material for 26 million years, accounting to 86% of the Earth's mass. So again, this is getting us to this point of a rapid growth to, I don't know where Bill came up with the 60% is the full Earth or something, but whatever. So you get almost 90% of the Earth in a very short time period of 26 million years, and you're growing it out of volatile poor material. After that, then, what you're left with is an Earth that has a silver isotopic composition that's very different from what we measure today for the Earth. So you have to bring that down. You bring it down by adding a volatile rich component, a CI component here, in a 4% of the mass of the Earth. You add it sometime after 26 million years, because after 26 million years, the manganese-chromium system is shut off, because manganese-53 is gone. So you're no longer under the constraint of the volatility issue. So you can add it volatile-rich material this late. That drags the silver down here, and then this model was used to account for a late giant impact in the formation of the moon. But it turns out the palladium-silver system isn't sensitive to that, so you could have it either 30 million years, 60 million years, or 80 million years. You have to add it sometime so that you drag the silver back down into the range of the Earth's mantle, but when is not really defined by this point. So this is a non-unique model, like many of the models that we've seen so far today. But what it does, though, is it provides you some of the flavors of what must have happened during the Earth's growth. It started from a very volatile poor material, and it changed. That composition of what was accreting the Earth changed with time from volatile poor to volatile rich. It's mostly volatile poor. We know that based on its composition today, so this all fits with that. And then you could add this material later in Earth history. Yeah.
I think contrary to what you said, there must be some program in the Earth's core.
It will affect the manganese chromium system only if that segregation occurred while the system was still alive. It's a 3.5 million year half-life, so it would have to occur very quickly.
Chromium must go into the core very early when conditions are very...
That can affect it, but not enough to alter the manganese chromium isochron that I showed you. Basically, what it's going to do is it's going to broaden the range of the estimate for the manganese chromium ratio for the mantle. But you know the chromium isotopic composition of the mantle. So the answer is, well, first off, we don't know how much chromium can go in the mantle. But well, the answer is it can affect it, but it's not going to affect it to the point where it's going to change this argument.
I'm confused about what volatile you're talking about. Are you talking about silver as a volatile?
I'm talking about silver. This is where we got into the terminology issue. Is that silver to a geochemist is a moderately volatile element. Manganese to a geochemist is a moderately volatile element. Both hafnium and tungsten are refractory elements. So what I'm talking about here in terms of volatile poor means it's poor in silver in this case, and it's poor in manganese. So those are the two constraints that are driving you to this volatile poor statement here. And here the volatile rich stuff, again, we're talking about adding silver and we're adding manganese at that stage.
And how close are manganese and silver on the condensation?
Let's see. Manganese is here. Silver is here. So silver would be down here. So these are in the moderately volatile category. Whereas there's chromium and phosphorus up here. And hafnium and tungsten are going to be up here. There's tungsten. Is that tungsten? Yeah. And there's hafnium. So those are really refracting. Yep.
Go back to
That one? Next one.
yeah. So here you have the ratio of twice as C.
Right.
Where do you have the C coming from? Where do you have the C?
You have, like with the hafnium tungsten system, you have this point that you get from meteorites as the initial silver isotopic composition of the solar system, and you have this point, which is the present-day silver isotopic composition of the Earth's mantle. This actually, what's shown here is exactly the model that I showed you yesterday in the hafnium tungsten system. It's from Francis Nimmo's approach to do the the accumulation model, and basically with every one of the accumulation events you allow a core forming event. So no, absolutely not. No, I mean, that's what I tried to show you yesterday in the hafnium tungsten thing, is that you only know this point and you know this point, and how you get between those 2 points is an issue. But I don't think it changes the general conclusion here, is we're looking at core formation occurring in tens of millions of years after Earth formation, and it doesn't affect this issue about the transition from volatile poor to volatile rich accumulating material. How, the details of it are not there. Well, this is the addition of by what you're doing here is you're adding silver.
But the reason that you say you need it is to explain manganese chromium.
No, you're needed to explain the silver, because if you start with a volatile depleted object, its silver isotopic composition is evolving outside of the range of the Earth's mantle. So what you need to do is to drag that point back down to the range of the Earth's mantle, and the way that you do that is by accreting a volatile rich meteorite that has a low palladium silver ratio that has unradiogenic silver in it.
It could be done in steps rather than...
It could be done in steps. Yeah. I mean, this is pretty much after, this is after manganese chromium is decayed, so you have no controls left for manganese chromium on this. This is already at the very end of the palladium silver life as well. So this actually represents the ingrowth of the radioactive species, and you have some constraints on that. These are all just mixing events after they've decayed away. And so that's why, like in here, you could, any one of these giant impact events will do the same thing to you.
And with respect to the giant impact, you're adding the mantle and differentiated impactor?
Here again, you're dragging it, no, you would be dragging it down, so you'd be adding volatile silver, so another volatile component at that stage. Anything that lowers the silver here has to be from a low palladium silver object, so volatile rich object.
And you cannot imagine an extreme case where you just stop the event, like stop the here. You have to stop there, like, and then you go.
Yeah, but it turns out that if you had a chondrite evolution that went up like this and went over, that was what I showed you in the CI evolution here. So you can get that. So it turns out the Earth and CIs have exactly the same silver isotopic composition. So that would be this case that you're talking about. But the trouble with that is that CI chondrite is this point out here. So you can't tolerate that volatile rich material that early.
How strong constraints the 26 millimeter? Can you push that?
No, I mean you know, the numbers are not a terrible constraint. Moon rocks, no. Something NASA giving you 20 grams of lunar samples is not really in their bailiwick at the moment. Alrighty, so I hope I've completely confused you on this point so that you think we know what we're talking about. So we formed the core. We had this core extracted out of the silicate earth. And I brought the issue yesterday is that we have the evidence that there was a late veneer. So there was something added to the earth after the core formed and didn't equilibrate with that. Here's another way to look at that. Here's a ratio of magnesium to nickel. So nickel is a strongly acidophile element. There's probably many weight percent of nickel in the core. Magnesium is not soluble in the core. So we're looking at an element where the magnesium-nickel ratio in the core is 0. The magnesium-nickel ratio in the mantle is something like 120. What's shown here in the data are peridiotites, so pieces of the mantle from various stages in Earth history. So the Kafal Craton in South Africa, this is an area erupting 2.9 billion-year-old pieces of mantle. The premier kimberlite, again in South Africa, is a 2 billion-year section of mantle. There's some younger stuff here in China, and then modern abyssal peridiotites out here. What you can see on a diagram like this is that the magnesium-nickel ratio of the mantle hasn't changed over at least the last 3 billion years of Earth history. Now, this is actually a pretty sensitive indicator of how much core you could tolerate. If this is the primitive mantle point, if you added 1% of the core of the mantle mass back to the primitive mantle, you would lower the magnesium-nickel ratio to there. So you can't even tolerate a 1% re-addition of the core into the mantle. And similarly, if you're going to keep extracting siderophiles into the core, you would lower the nickel in the mantle, and you would expect the magnesium-nickel ratio to rise, but you don't see that. If anything, you actually see it going down a little bit. So this is evidence that once you form the core, there was a period where it was probably communicating with the mantle, but then that period shut off. And since that time, for the last 3 billion years, the mantle and the core have been chemically separate systems. Well, I mean, siderophile elements are the most sensitive tracer of that. I mean, this issue that, magnesium nickel's in the core, it's 0 in the core, and it's 120 in the mantle. So it's a very sensitive indicator if you add the core back to the mantle. You just can't make those kind of statements based on lithophile elements. First off, there aren't any in the core. So, yeah, I mean, it's basically how much metal you could re-assimilate into the mantle. Yeah, Bill?
The only other additional factor I would suggest, and this might be what Sarah's thinking about, this is for samples we can measure. So if you're at all thinking about phenomena happening at the core mantle boundary and they never come to a geochemist's hand, we can't constrain it. But if we've touched it and measured it, we have a constraint, but that's valid.
Yeah, that's valid. Yeah.
Also, I'm not a fan of the models that say that there's been core mantle interaction. But I think that people who prefer those would say that there's some select rocks here and there that show an imprint, not that all of the mantle, but some small reservoir.
There are, and if you look at like 186 osmium arguments and whatnot, I mean, there's a lot of debate about whether that's a core signal at all. So there's that issue. The other one is the manganese-iron ratio in Hawaii, for example. I mean,
So, it seems to me this is an argument that the bulk mantle, on average,
has not.
Effectively no core.
Yeah.
But it doesn't eliminate the possibility that there are some select reservoirs.
Well, the 186 osmium is sensitive down to the per mil level. So the kind of range that they see in 186 osmium, assuming that all the estimates of core osmium are correct, could be accommodated by a per mil addition of core. But if you think about a per mil addition of core to each plume, then it doesn't take, it takes you 10 plumes to get this 1% of the core added back to the mantle, and I don't think it works in the long run.
There are also these ideas of continuous core formation, like the decomposition of peroxide using metallic iron.
Yeah.
It will bring core material to a metal material to the core and vice versa.
Right.
So they could cancel out and you don't see the net effect, right?
Well, I mean, you'd have to regulate the transfer so that they do cancel out. I think it would be unlikely that they would cancel out. So, that's the issue. I think the way out of that is the one that Bill brought up, is that this might be occurring at the core mantle boundary, but it's not getting that signal up in the upper mantle. I actually doubt that because I think there's whole mantle convection, but anyway.
Not just one ratio. So
Yeah, no, I mean, there's a zillion of these. That, yeah. All righty. Michael.
The late veneer you talked about on Monday has been well stirred into the mantle after 3 billion years.
I'll get to that in a couple of slides. The answer is no. By 3 billion years, it hasn't been, and I'll show you why. All right, so we spent a lot of time, and in fact, I ran out of time in my introductory talk to talk about the silicate Earth, which is most of what I do for a living. So I may run out of time with it today as well. But what we'd like to face then is the issue of what was going on in silicate Earth. So we formed a core, we formed an Earth that's volatile depleted. Did the early Earth look like this, the hell on Earth type of model, really hot? Or I think the more correct approach is that it may have looked like this within 500,000 years after a giant impact, but a couple million years later it looked not too much unlike what it looks like today. Although I don't know a place that looks like that today, but so what we can look at then are to look at the differentiation of the silicate Earth are these elements, the refractory lithophile elements. Rubidium is not refractory, but most of these are. And what I showed you yesterday is that when we look at the rocks that we have under our feet, so the continental crust shows a very non-chondritic pattern. Chondritic patterns, they have to be flat at once, so these are partial melts. But so you're looking at flat patterns for a chondritic estimate of the Earth in these elements. So the continental crust shows this strongly enrichment in the most incompatible elements, and the oceanic crust shows this complementary depletion in these elements. So we're looking at in the rocks that we can sample right under our surface have had this history of chemical fractionation due to partial melting. This order, to get smooth patterns on these diagrams, it's important to recognize that you can arrange this order any way you want. This order is arranged based on the way that these elements partition during the partial melting of mid-ocean ridge basalts and ocean island basalts. So basically, to get smooth patterns on this, you have to be melting in the shallow mantle, where clinopyroxene is the main phase that's controlling these elements. So that's sort of the relation you get here. Lead probably represents some funny business with the way that subduction occurs, and lead comes off of subducting slabs. We don't need to go there in this talk. But the wisdom then is that if you combine this in the right mass proportions, which is what we're going to do tomorrow in the tutorial, you'll end up with a pattern that's perfectly flat, going back to the primitive mantle before differentiation occurred.
What causes the depletion in niobium in the crust, but we don't see a complementary?
That's a good question. That's a good and tough question. There's a possibility that niobium is partly siderophile, particularly at the reducing conditions and high pressure. So some of that could be in the core. There's also, it's debatable. The other issue, though, is that in the process that makes continental crust, which is probably island arcs, it turns out that elements like niobium stay behind in the subducted material, whereas the elements on either side of it come off in the fluids that are introduced into the wedge above the subducting plate. So that's another way to create this fractionation, and it's probably unique to that. And then you have to have some other complement. So it's a good question, and when we have an hour together, I can explain the options to you. It's a point of debate among the community. So the idea, though, is that you can add these back together to get a flat pattern. But in fact, when you look at mantle rocks that on many other constraints, particularly major element constraints, are assumed to be primitive, so represent the best estimate of the primitive mantle composition.
What's the primitive mantle? How do you get the primitive mantle?
Bill will cover that. I mean, yeah, I mean, in terms of elemental compositions, there's a long story that gets you to this point that Bill will cover tomorrow.
Don't worry, it's easy.
Yeah, it's easy. so when you look at mantle rocks that have major element compositions that you think are primitive, you do in fact get these nice flat patterns up here for most of the incompatible elements, but you always see this depletion in the most highly incompatible elements. So it's actually hard to find on Earth a rock that has a perfectly flat pattern. So if that, if there is the primitive mantle that is characterized by this perfectly flat pattern, it's a pretty hard thing to come up with. So I'd like to address that issue. I mean, this might just be the fact that these have lost a little bit of melt from your primitive mantle, and you need to know when and how that occurred. So we're going to look at, again, the samarium-neodymium system. This is particularly well placed on this diagram because it's right where this inflection occurs. So if you're doing some partial melting event that creates patterns like this, samarium and neodymium will be affected by that partial melting event. The other nice part about samarium-neodymium is it has two radiometric systems embedded in it. One is the 146 samarium, an extinct nuclide, decays to 142 neodymium, has a 68 million year half-life. So again, it was present in the early solar system, but it was gone by 200-300 million years into Earth evolution. And then it has the long-lived one here, 147 goes to 143, 100 billion year half-life, so you've only lost something like 3% of the 147 over Earth history. So it's still around. Every time you change the samarium-neodymium ratio of a rock in Earth history, it keeps recording it. Here, after 200 million years after the formation of the Earth, if you change the samarium-neodymium ratio, you no longer affect the evolution of 142 because there's no 146 left. So the reason that we go after the system, it's not a particularly easy one to measure, and the anomalies are small. If you look at other planets, you actually see quite large anomalies in 142 neodymium. So Mars in particular shows the biggest effects here, and these big effects in Mars are also, there's also variation in 182 tungsten in silicate rocks in Mars. So this is the origin of what we were talking about this morning about Mars forming within 3 million year time window. So it had to form and differentiate very early to create this magnitude of anomalies in 142 neodymium and in 182 tungsten. So this is the evidence that's providing the age of early differentiation of Mars. The Moon also shows variation in 142 neodymium. It's not as big as on Mars, and I'll show you why in a bit. But these are the types of evidence that lead us to the suggestion that the silicate planets differentiated the silicate portion of the planet early, while 146 samarium is still alive. If we go to the Earth, though, we can look at this diagram. It's from Matt Jackson's work. So this is all the published data on 142 neodymium in modern rocks. These are from various ocean islands down here. There's more been here somewhere up here. You see that there's no variation outside the air, which is that blue band. So in the modern mantle, everything has the same 142 neodymium isotopic composition. The only time you see 142 neodymium variation in the Earth is when you go back in time. Michael, this is the answer to your question. So here, these are 3.8 billion year old rocks from Iswa. They show a positive anomaly. These are what I think are 4.3 billion year old rocks from Nuvuagatuq. I'm sure you all know where that is. It's in northern Quebec on the eastern shore of Hudson's Bay. But these are two old terrains, and these old terrains, there's another one in Anshan, China. These are the only ones that show variation in 142 neodymium on the Earth. So we have the evidence from this that in the early history of the Earth, there was mantle variability in this isotope system, but in the modern Earth, it's not. So this is an example of mixing that early evolution away, or that early heterogeneity away. So with that system, though, because the two isotope systems include the same elements, anything that you do that affects 146 samarium to 142 neodymium also has to affect 147 samarium to 143 neodymium. So this is the 143 system here in time. What's shown here are 4 evolution curves with different time periods for the initial differentiation. So if you wait 5 million years and you form a samarium-neodymium ratio of that number, chondritic is 0.196, so this is a little bit high. The longer you wait to do this kind of an elevation of the samarium-neodymium ratio, the higher you have to make it, because by 100 million years, you've already lost more than half of your 146 samarium, so you have to increase the samarium-neodymium ratio to make up for the decay of the 146 samarium. So all 4 of these will produce a 20 part per million difference between chondrites and the Earth's neodymium isotopic composition. But over the long term, because you have to change the samarium-neodymium ratio, they result in different evolutions in 143 neodymium. So today, the highest reservoir that we have available to us is the mid-ocean ridge basalt source. It's up here at something like plus 10 or 12. So you can see that if you waited even for 100 million years, you would need a samarium-neodymium ratio like that to explain the 142. You would evolve off to isotopic compositions that are above those that are seen in large volume reservoirs on the Earth. So we can't tolerate this kind of a delay in the differentiation that produced the 142 neodymium data. So then we can look at it. So here, for example, this comes under this. This is a 5 million year, actually a 0 million year would be about the same. So very early differentiation will produce a neodymium isotopic composition in 143, about here, 6 or 7 or 8, versus 0 for what we would expect for chondrites. If we actually look at modern rocks, this is a histogram of the neodymium isotopic composition of ocean island basalts. You can see a lot of people put a lot of time into this one, over 30 years of measurement. We've singled out Hawaii here. This is work Matt Jackson and I did from Hawaii, just because there's a lot of data from Hawaii. We didn't want to biasing the histogram, but you can see it really doesn't. But the point being is if you had a chondritic mantle, it should be here. And in fact, what you see is the major peak of this is occurring at these higher values that are perfectly consistent with this value that's predicted from 142 neodymium excess of the Earth compared to chondrites. Now you can explain this curve, and there's been these various transport models between a lower mantle that has an epsilon neodymium of 0 and an upper mantle that has an epsilon of plus 10. And you just have to regulate the amount of mass transport between these reservoirs. So basically, if you have a mid-ocean ridge basalt source up here and you add a certain amount of a lower mantle at 0, you will drag that value down. Those models work. So I have no criticism of those models except the fact that I don't think that they're right. I don't think they're the way that the Earth works. Numerically, they're correct, but physically, I'm not convinced of it. There is this issue. When you start comparing these things, I showed this yesterday. Here's the neodymium isotopic composition versus other isotope systems that are also tracers of primitiveness, helium-3,4 in this case. I showed this. Here's your chondritic reservoir. If you think of high helium-3,4 ratios as the most primitive, the actual highest helium-3,4 ratios on the Earth occur up here in Baffin Island, not down here at chondritic neodymium. So again, the suggestion here is the primitive reservoir is in here, not down at this end of the diagram. And then if you look at the rocks that are in here, in particular, ocean island basalts, these are the flood basalts that Matt and I worked on again. This is the whole ocean island basalt data set in neodymium versus lead, just to throw in another isotope system to confuse you even more. What you see is this huge range in lead isotopic composition here, but the samples that have the neodymium isotopic composition within this non-chondritic mantle from large igneous provinces like Ontong, Java, and the North Atlantic flood basalts and so on, they're all labeled here. You see plot up in this region, partly by definition because we're forcing them to fit in this thing. But if you take the lead isotopic composition of those rocks based on the neodymium constraint, and you look at them in a lead evolution diagram down here, 7 to a 7 to a 4 to a 6 to a 4, what is shown in these diagrams these are single stage evolution ages from an initial Earth of 4.5 to 4.43 billion years. And you see these data actually plot well within that kind of a range of ages. So the suggestion here from the lead as well is that these represent derivation from sources that formed more or less at 4.5, 4.45 billion years ago. Whereas these rocks, the rest of the ocean island basalts here, scatter out along this trend that's called the Northern Hemisphere regression line. This has a slope of about 1.8 billion years. So a lot of the ocean, Steve, this is what I was talking about earlier. A lot of the ocean island basalt data lie along this 1.8 billion year curve, but this select group of these large volume flood basalts may sample primitive mantle that's just not chondritic mantle. It's something that was differentiated around this 4.45 billion year time window. Now this is an interesting time because I've spent the first 3 quarters of my talk trying to convince you that cores formed within a couple million years or maybe 10 million years. And here we're talking about a silica differentiation of the Earth, and in this case I'll throw in the moon, that's more like 100 million years after solar system formation. So this is 142 neodymium for a variety of lunar rocks and also the Isuwa rocks from the Earth, versus 143. You could think of this as samarium-neodymium ratio basically. And you put in all these lines because you don't want people to see how bad the scatter is in these data, so it confuses a lot of that. But the point being, the only thing I want you to take out of this is that this includes lunar crustal rocks here, it includes creep basalts from the moon, and it includes Mare basalts from the moon up here, and it includes these Isua samples from the Earth. And the only thing that's important in this diagram is if this differentiation that occurred, changing the samarium-to-dimming ratio basically, if that occurred at 4.56 billion years ago, those rocks would lie along that line there, t equals 0. They don't. They lie along something that's much shallower sloped, suggesting that this silicate differentiation of both the Earth and the Moon didn't happen at 5 million years after solar system formation. It happened more like this. And again, treat these errors as this is dominated by lunar data. Yeah, there's not enough 142 variation in Earth rocks to come up with something like, although the Isua data provide the same type of model ages. So, but you can see that the level of fractionation of the Isua stuff isn't enough to define this. For the Moon, it is. So the lunar data is very hard pressed to fit 4.55 type ages. In fact, there's a lot of isotope systems that don't allow the Moon to be that old. All right, so.
Similar to the Borg, they also have late night motion crystallization.
Yeah, I mean, yeah, that's my paper. So yeah, that's actually this data set here. So yeah, that's the answer. But the point being is that this 120 gives you the ages that are more like 4.45 than 4.55. So if you've seen through a lot of the talks so far in this session, there's this sort of implied opinion that lunar formation, the giant impact, occurred 100 million years after solar system formation. This is why. Okay.
What is the Isua example?
This one, I don't know. I mean, these are, you can see the error bars here. Analytical issues with these are big. It's one out of many. I don't know why it's up there.
Could this also imply that the giant impact was not as giant in the core, for example, and it only affected the mantle of the Earth?
And the Moon. So, yeah, the one thing we see is on the Moon, these are the oldest ages we get. There are older lunar crustal rocks, but the chronology on the lunar crust is incredibly poor. So when you look at planetary evolution models, these are the kind of ages you get. You don't get 4.55 ages for. All right. Now this, again, Michael, this is the answer to your question. So I mentioned earlier on that you do see 142 neodymium variation in terrestrial rocks, but only in really old ones. So here's a plot of age, and here's the actual data. This is a series of rocks from Isua from a number of workers. Most of this data is actually from Vicki Bennett. What you see is this is the modern terrestrial value here at 20 parts per million above chondritic. So you see these values here that are even higher. There is some suggestion that they decline with time. So again, here's another one of these non-unique models that we've been seeing a lot of in the core formation. But in order to get up here, you have to have an even higher samarium-to-dimming ratio than we've been talking about to get to this value. So if you had a very high samarium-to-dimming ratio, this comes from some lunar modeling that Maud Boyer and I did. But these numbers aren't critical except the fact that they need to be higher samarium-to-dimming ratio. So you start that instantly, you evolve up to some value up here, and then at some arbitrary value you start mixing it with the chemical complement of this that has a low samarium-to-dimming ratio, is evolving off the bottom of this diagram. And you drag these data back down to the modern value here. So again, this is a completely arbitrary model. I mean, you just adjust both these kind of numbers and these time periods just so that you get this mixing curve that fits the data. So that, there's nothing really thrilling about this, except that this system is coupled to the 147, 143 system. So if you come up with a silly model to explain the 142 neodymium data in these, then you create a curve, or a curve like this for the 147, 143 system looks like this, and these are the data from mantle-derived rocks through time. So you see you need this initial rapid evolution of 143 because of this high samarium-to-dimming ratio to get up to the values that are seen in early Archean rocks. And then it looks like you need to drag it down, which is what you need to explain the 142 data, back to a sort of an average terrestrial value here, and then it evolves up like this. And then this additional offset to the higher values in recent time are because you've taken continental crust out as well over time.
Beyond 4.0?
No, because we don't have rocks older than that.
How do you know that it went up?
Well, you assume that it had to start from chondritic when the Earth formed. I mean, that would require a different solar system, initial 143, which is a nucleosynthetic issue that would be tough. Alrighty, so this is the evidence that there was heterogeneity present in the early Earth that may or may not result from a magma ocean differentiation. and it actually mixed away over this sort of first billion-year history of the Earth. So one of the possibilities to explain an evolution like this is from Lindy Elkins-Tanton's work, my current boss, is that you start with a magma ocean, you allow it to fractionally crystallize, and what's shown here actually are density contours. So what happens is you crystallize magnesium-rich minerals at the bottom, which are relatively low density. This is a case for the moon. This may or may not be true on the Earth, but so low-density minerals at the bottom. They exclude iron oxide, so basically you concentrate the iron oxide to the last residual melts that form up near the top. So these melts end up being very dense, or the rocks that form from these melts are very dense. So you start out with a situation at the end of magma ocean crystallization that has the cold, dense stuff on top of the hot, buoyant stuff on the bottom. This, of course, is a dynamically unstable situation. It undergoes this kind of a turnover, and you end up plating out what was originally the crust at the bottom of the system, and actually this becomes a stable, convectively stable stratification for a long time, because you have dense cold material at the bottom and hot buoyant material at the top. So it actually can take a while to overcome this kind of thing. So if you look back at this evolution, that was part of the reason behind this, is this idea that you had this magma ocean overturn. So you left the upper mantle with this very depleted reservoir, and you began to mix in some of this stuff that was what was segregated to the bottom. So that's the origin of this type of model. And this may or may not be the correct answer, but it gets to this point that the end of the magma ocean, the end of the accumulation, isn't the end of the story.
That's not so much an idea.
This is working to, I mean, this is inhomogeneous as it gets, right, at this stage. And what's going to happen is eventually this thing warms up and establishes a convective system. I mean, it will overturn the geotherm to the point where it becomes convectively unstable. It starts convecting, and the convection does the mixing of these layers, assuming you don't assign them massive density contrast. This happens very quickly. I don't know how, I mean, very quickly meaning I think under 1 million years even. I know somebody more familiar with these models than I am, but this is a very, very quick overturn. This is a very, very unstable density configuration.
Depends on the viscosity,
yeah,
which we don't know.
But I don't understand the heterogeneous.
Well, I mean, this again gets to the stages of accretion. If you think about heterogeneous accretion as that model I showed of adding 26% of the, or 86% of the Earth in 26 million years, I would think that in each step of those you're getting a magma ocean, and this is probably the story from the last magma ocean event. By this time you've mixed out.
Right, so the magma ocean here is not.
I would say that at this stage you've got the Earth. So you're talking about the end stage of the Earth by the time you get to we're assuming that this occurs at 4.45 billion years, not 4.55 billion years. So when this is the giant impact, if you will, or the result of the giant impact, this is taking what was probably a more or less homogenized, subject to the constraints you talk about about the mixing, which I think are good issues. But that whole history of the heterogeneous accretion has been stirred away by the various violent events getting up to this point. Presumably it's quite happily staying where it is, right? Hot, molten, and happy to be dense.
How is it?
What core?
Well, there's a big core.
Yeah, that's this hole right here, Bill, that white thing there. So.
Oh, we definitely know there's a core on the moon?
Oh, yeah, I mean, this calculation is for the moon, but it's a valid question. The answer is that heat coming out of the core would only help to start this overturn quicker, right? So this is the overturn. It sets up this stable temperature gradient. So it's cold at the bottom, but yes, it's sitting on top of what's probably a superheated core. So that's going to help warm this stuff up and start the convection sooner. That's going to erase this.
Just a question. I mean, the initial stratification is the idea that you sort of layer this in statically and then you turn the dynamics on afterwards?
Yeah, no, and what this is that, I mean, if you think of the Bushveld intrusion or any layered mafic intrusion, that's all that this is. So what Lindy started with was a totally molten moon in this case, and put it to a phase diagram, let the olivine come out first at the bottom, track the evolution of the liquid, pyroxene saturates, which is probably the green band, and so each one of these bands represents the onset of a new mineral that's crystallizing, resulting in a solid rock that's got a little bit different density than the last. All the way through this sequence, you're fractioning the iron oxide into the residual liquid. when you see this in terrestrial layered mafic intrusion, you end up with a top rock that's just chock full of iron oxides and titanium oxides.
I guess I wondered whether in a planetary scale problem like this, where you wouldn't actually start to see some dynamic overturn before the crystallization process.
Yeah, I think that's a very important question. Yeah, I mean, this is a very static example of a magma ocean. So this is a layered mafic intrusion model, but whether a planet scale does this is a good question.
Just to add to that, this assumes we know how magma oceans crystallize.
Yeah, on the moon, I think we can do a reasonable job of it. On the Earth, yeah, we don't have a clue. Yeah, no. I'm running out of time. So let me come up with one thing that I think you might find interesting. So one way to do this sort of early magma ocean, there's a couple ways to do it. I talked about this yesterday. One is sort of the lunar analogy, where you melt the whole mantle and you allow this type of differentiation that's shown in the last slide, where you fractionate up the iron-rich liquids to the top. You form some sort of, on the moon it's called creep. On the Earth, I don't know what it would be called. But so you get this residual liquid up here that's very dense and overturns. And you have to endow it with enough compositional density to just stay down there, because this is a missing reservoir. This hasn't come back in at least in significant quantities over Earth history. So this would be basically a low pressure type of fractionation scenario versus this one, which is where you have the basal magma ocean. This stuff that's crystallizing down here, this is the magma. What's crystallizing out of this are going to be perovskites, not clinopyroxenes in the uppermost mantle. There actually may be a way to tell the difference between these two that one can do based on looking at the pattern that we calculate for this reservoir that's predicted by the neodymium isotope data. So this is a plot from Matt and Mark Jelinek that shows this red pattern here is what we calculate for this non-chondritic primitive mantle, if you will. This is the same pattern I showed you yesterday. You're looking at sort of 60 to 70% of the abundance of the heat-producing elements. Potassium's on the diagram this time. So whoever asked about that yesterday, it's here this time. So potassium, uranium, and thorium. So you have a pattern like this. And I mentioned earlier that the order of these elements is dictated by their incompatibility during melting in the shallow mantle, just because this was done by people who were looking at ocean island basalts. So the fact that you get a smooth pattern here is interesting. Yeah, it was rejected, but I mean, this pattern has been published, I think, 3 or 4 times now. So it must be right? It's published. So the point I'm going to make is still correct, Matt. So the point here is, if this is what the primitive mantle looks like, what do you have to take away from a chondritic composition to get a pattern that looks like this? These patterns in a silicate differentiation scenario are going to be dictated by the distribution coefficients of the phases that are coming out of that liquid. So if you look at some of the possibilities, so here's what would happen in the shallow mantle. The main phases affecting these elements are going to be clinopyroxene and garnet. So garnet has these are distribution coefficients. So this is the amount of the element that goes into the solid versus the amount that stays in the liquid. So garnets concentrate the heavy rare earth elements in particular, don't like the light ones at all. Clinopyroxene sort of doesn't care about it until you get to this end of the diagram. So if you compare these patterns versus this is a published version of this pattern. What you see is you don't see something that looks like this. You don't see strong fractionation among these elements. So it's not consistent with the extraction of garnet. So even getting into those kind of phases, it actually fits the clinopyroxene pattern reasonably well. I mean, there's lots of wiggles in here, and we're never going to get a one-to-one match. But it shows this sort of flat evolution on this type of order that looks a lot like that part of the diagram. So this is what led us originally to suggest that this reservoir, non-chondritic reservoir, is produced by low-pressure processes where clinopyroxene is dominating. If you think about what happens when you fractionate perovskites, so here's this is Bernie Wood's data for Cornier and Woods for the distribution coefficients for magnesium and calcium perovskite. So these are the phases that would be fractionating in the lower mantle. So if you're doing this in a basal magma ocean, the interesting feature about these phases, so look at magnesium perovskite here. This pattern, if you forget about these big positive spikes, this pattern looks a little bit like garnet. So right there you got a problem matching this. But more importantly on this pattern, so here's the rare earth elements coming down, and then you reach what's known as a high field strength element, hafnium. It's got a high charge cation. You see that magnesium perovskite actually likes it a lot, whereas then you come down to the other rare earth and you come down to lead. It likes lead a lot. It likes niobium a lot. So if you fractionate this, you're going to create a pattern that looks like this or its complement, and that's not what you see in this kind of a pattern. So you can't tolerate much fractionation of magnesium perovskite alone. If you look at calcium perovskite, the other phase, it actually is very complementary to this. So it has a fairly flat pattern among the rare earths, and then it really doesn't like hafnium, it doesn't like lead, and it doesn't like niobium. So yeah.
I'm just wondering, when you crystallize perovskite in the lower mantle and you have a particular set of partition coefficients for it, then you bring that perovskite towards the surface and then it goes to phase transition. And then you melt it, it's going to have a different set of partition coefficients, but the abundances will be set by the original partition coefficients. How do you sort that out?
No, actually, a phase change will not affect these compositions, right? So if you take a material that has this composition in the upper mantle and you put it in the perovskite stability, you're not changing this distribution, because as long as you don't allow an open system, right? Because you're conserving these elements. So even though it's in perovskite, the perovskites are going to have to find some way to deal with that pattern. If you're going to fractionate one of these, so if you fractionally remove one of these mineral species, then the residual liquid that left behind will have to have this imprint of the distribution coefficients. But if you just do it through phase change, and you don't lose a component, I mean, the intermineral fractionation will change, but the overall abundance in the rock won't. Alrighty, so the point being is that it's clear that you didn't fractionate either magnesium or calcium perovskite to get this pattern. There is this interesting caveat, though, is that if you combine these two in a petrologically reasonable amount, so a 90 to 10 mixture of magnesium and calcium perovskite, you end up with this red pattern. And this red pattern, okay, does have some wiggles in it, and maybe we could get rid of those if we change the 90-10 a little bit. But you're ending up again with a pattern that's actually fairly flat, and it's starting to look like this. So I don't think we can close the door yet on the basal magma ocean, but I think the most obvious case is that, in fact, this kind of fractionation is done in the shallow mantle. With that, I'm actually done. See, conclusion slide even. So, if you want to postpone lunch, I'm happy to answer questions. If you don't, those are the conclusions. This will be up on the web as soon as we can get it up on the web. So, thanks much.
Rick, what were the pressure or temperature conditions of those distribution coefficients?
These are, Dave, you can probably help me with this. These are multi-anvil measurements, so I think they're probably just in the uppermost lower mantle, if I'm not mistaken.
So do you think things could be sufficiently different at the base of the mantle that this might not be a really serious problem?
Yeah, there's two things actually with the basal magma oceans. One is understanding the phase diagram and the melting relationships at those pressures. Well, there's lots of things. Two is understanding the density of the melts. Three is understanding what these partition coefficients change as a function of temperature and pressure. The third is it's probably not only these two perovskites that are involved, there may be magnesium-woostite. So you've got to do a realistic model of what's likely to fractionate down there. I just threw this up as an example of a way that you might use this composition to decide between a shallow and deep origin.
In case of in the plot for uranium and lead isotope, so we saw larger variability in the lead isotope, so modes and all kinds of stuff. How far is the mobility of lead affecting that, for example, this isotope?
Shoot, where was it? It's this one. Yeah, so the question is, let me see if I got this right, but the fact is that there's this huge range in lead mobility as opposed to what you see in just this set of rocks. One of the issues with lead is that lead is an element that's very strongly concentrated in Earth's crust, in the continental crust in particular. So it is an element and hence an isotope system that's very sensitive to the recycling of crustal material. So a lot of this spread, I would argue, and been argued long before me, is a result of subduction of crustal materials back into the mantle. So one idea is that if the primitive mantle is sitting down here, this trend has been caused by subduction over the last 1.8 billion years, is dragging the lead isotopic compositions out in this direction. That's also an explanation for how you can get down to lower 143, because the continental crust will have like values of -20 or something down here. So I think that's the explanation for lead is very sensitive to crustal recycling. I think there's the answer to that is I don't have a clue. I mean, that's the correct answer, but the answer I'll give you is that the Cornier and Wood partition coefficients were measured in a material of pyrolytic composition, basically, if I'm correct. So they are measured in an upper mantle oxidized peridotite composition. So what they would be in if you're talking about starting with an endocyte chondrite or a more reduced thing, I have no idea. I mean, that's an important factor. If we're talking about these heterogeneous accretion models, and we are in fact forming from a volatile, poor, refractory, rich, reduced material to begin with, then the evolution may be very different.
When you're talking about helium versus helium isotopes, is it possible that those two systems
They could. I mean, there's always issues on these diagrams because mixing is not only dependent on isotopic compositions, but also on the abundance of the element. So if one of these reservoirs has huge helium concentrations, but not huge neodymium concentrations, then you could see an effect by mixing it in on helium, but you wouldn't see it in neodymium. So there are ways around it. I mean, this has been known for a very long time, but I think, to me, the interesting part is that we've changed our idea that we used to think the primitive Earth had to have a chondritic neodymium isotopic composition. And in fact, a lot of the arguments when you didn't have that was, we've got to have some primordial component or something missing. But in fact, the 142 neodymium results suggest that the primitive Earth neodymium isotopic composition may well be up here, which then is perfectly consistent with the high helium-3. So these are, I think, supportive of one another. There are ways, like in this diagram, these rocks don't have epsilon of 0 either, and that traditionally has been explained because you've controlled the epsilon of 0 material in the lower mantle, and you're only allowing enough of it to get through where you drag the upper mantle values from here down a little bit, but not down to 0. So there are multiple ways to explain these, but I think the more systems that you can combine to get a consistent story through all these is pointing us in the direction of a non-chondritic Earth composition for the primitive mantle.
Do you think it's in your lead-lit plot of high 3-4 source salts? Do you think it's significant that those on the plot on the northern hemisphere reference line at all? Is that?
Yeah, I think it probably is. If this is a primitive mantle, this is the differentiation from the primitive mantle. So, yeah.
But then I guess, can you change your uranium-lead ratio significantly from the formation of high 3-4 basalts to the formation of those later? If you have continual lead extraction in the continental crust at the time, would they plot on the same reference line?
Let me think about that. I mean, the point on a diagram like this is that any reservoir that has maintained a constant uranium-lead ratio for 4.5 billion years will plot somewhere along these lines depending on what that uranium-lead ratio is. So low will be down here, high will be up there. So if you've got a more or less homogeneous primitive mantle down here that formed at 4.5 billion years, if you then have some fractionation event in it later, let's say 2 billion years, then you're going to create slopes emanating from that area that will have the lower slope. So you'll have sources that have that lower slope. Is that addressing what you're asking?